And you know, one of the things that I discovered, which I was really excited about with Professor Jonathan Swinton that led on this experiment with me, was that Turing was this amazing runner. And to discover things like that if he'd not been ill, he would have been someone that ran in the Olympics. So this is an incredible role model, I think, for young people, and that teachers could be using in the curriculum. Obviously, from the poets this morning, I was really excited by that line, adapt, change or die. And this is something that obviously challenged Turing in a way, because with the incident that happened where his lover was discovered and he ended up being charged, there was a burglary in his house in Manchester, and he was charged with homosexuality, and he had the choice to adapt, change or die, really, I would say. So he opted to have this therapy treatment. There's lots of theories about why he committed suicide, why he took the cyanide and killed himself, but I think that is one thing that's really important to be thinking about, this idea that he took these hormones that would potentially change him and reduce his desire for men. So with that in mind, that there's this life cut short back in 1954, but the other exciting thing that he was looking at that we didn't realise at the time was that he was looking at mathematical patterns in nature. And some of this data was discovered in one of the computers that he was working at here at the University of Manchester. And that, we thought, in 2012, or Jonathan Swinton thought, would be a fantastic way to celebrate his legacy in 2012. So, everyone will have heard this story, that he was found dead, life cut short. He had all these incredible contributions. But what I wanted to kind of focus on was a bit of that scientific legacy and the unknown bit to do with number patterns in sunflowers and the experiment that we ran last year. So whilst I'm talking, what I'd love you to be thinking about is I came across this best practice guide. I wish I'd found it a year ago, but I think it's being launched at the conference. And what was fantastic for me was to look at ways in which you can find positive role models and using those in school. So it's kind of think about this talk and ways in which positive role models in terms of Turing can be brought into the classroom. I'm not used to the mouse thing, I'm an iPad person, so I'm always like touching the screen. Try not to do that. So Turing sunflowers. Okay, so this was an experiment that was led by Museum of Science and Industry. Who's visited? Oh, that's good. Come back. Manchester Science Festival and the researchers at the University of Manchester, mathematicians and computing scientists, and Manchester City Council. And the idea behind the experiment came from this guy, Professor Jonathan Swinton. And he's a computational biologist, so he actually was obsessed with Turing and the history of Turing, and he was also obsessed with the problem that Turing was looking at, and that was looking at the patterns that you see in sunflowers. So you can see that there are these spirals that run round the sunflower. I don't know if you can see in one direction, they're quite clear, but then you can also see them running in another direction. I'm going to pass around and have a look a bit more close up. I haven't got loads of these, but if you just have a look round whilst I'm talking. I'll put two there. Sorry for the camera. Does it help that I stand still?
No, I'm trying to film
you.
you.
Right. Okay, so back to the experiment. I thought the best way for me to show you this was to show you a little clip from a film that we pulled together, people that participated in aspects of the... Why do computers have to ask you questions, Turing? I bet you didn't have that problem with it. You just did lots of computations. Oh, it doesn't like that. It doesn't match it. Okay, don't ask me that again. Let's just play it.
You need to just shut up and get on with it.
Yeah, totally. It still doesn't like it. Right. Great computer did not say no in Turing's time. Okay, there's another way to access it. There's another way to get there. Thanks to old man. Let's find it. It all worked perfectly fine in the rehearsal, but right, here we go.
Hi, I'm Nadia, the Manchester Science Festival Director, and this year we've got an exciting new project. You've heard of Van Gogh's sunflowers. Well, this project is Alan Turing's sunflowers.
Spirals of seed heads in a sunflower, you find 34 or 55 of those.
So you saw these patterns of numbers in plants?
That's right. And that was amazing because those aren't just numbers plucked from the air, those are numbers that mathematicians know about and have got a name for, called the Fibonacci sequence.
People growing sunflowers all over the world, here in Manchester.
Imagine a city full of yellow sunflowers. I mean, the visual impact is going to be incredible.
And that's it. Now you're ready to grow a cherry sunflower.
Sonny has grown absolutely massive, especially compared to all of the ones at school. These are sunflowers, 6 or more, growing outside our front door. Growing taller and taller every year. They have a real beautiful thing.
We are glad to be part of Alan Turing's fund from Jamaica, our home in the sun.
We are hoping to come to the Museum of Science and Industry in the autumn to count seed heads.
That just gives you a flavour of the project and participation behind it. And for me, one of the major challenges was seeing what people were doing. So I was working on this project part-time. I worked also at Lancaster University. And so the challenge for me really was to get people involved and participating in the project. And I didn't realise that people in Jamaica and South Africa and France and Paris and all over the place wanted to get involved in this project. Let's see, let's get back to it. Yes, okay, so on to the maths, okay? Okay, so if you could, the answer's here, so you don't need to worry. I know maths for some people was like, no. It was like, no for me. So let's start with what's a number that you can imagine in mathematics that's going to be absolutely very useful and didn't exist in some cultures for a while. What could you start with?
0.
0, okay, fantastic. All right, we're doing well. If you add 1 to 0, what do you get? 1. Okay, as I said, answers are up here. cheat sheet. If you add 1 and 1, okay, 1 and 2, it's a bit louder.
3.
Okay, 2 and 3?
5.
Okay, so along here, 1, 2, 3, 5, that is the Fibonacci sequence. It starts with 0. So it starts 0, 1, 1, 2, 3, 5, 8, 13, 21. Anyone here could tell me what's happening from one number to the next in the sequence? Other than you, because I bet you know the answer. You know it. Let's have someone else. Does anyone else figure it out?
It's adding the next two numbers together to get the next one. So 1 plus 1 is, 0 plus 1 is 1,
Yep.
1 plus 2 is 3, 3 plus 5 is 8, and then it's 6.
There you go. Perfect. Fibonacci number sequence. So what Turing and other scientists subsequently noticed is that in sunflowers, and Jonathan has picked out one spiral here so that you can see it more clearly, when you count round, so this is going round clockwise, you often get a Fibonacci number. So 55 is a Fibonacci number. If you count in the other direction, you on this sunflower you get 34. So 34, 55. Dare I go back in the sequence? No, let's not go back on the PowerPoint. Let's not go back on ourselves. But you will see that those numbers fall on the Fibonacci sequence. And so what we're interested in, and actually with this experiment, it's been done before. So it's not a new experiment. But one of the important things with science is that you replicate and you can repeat what happened before, which can be very boring sometimes, but can be very exciting because new things come out of that replication. So a Dutch academic did the experiment initially, grew lots of sunflowers, and he grew 319 sunflowers, and he was looking for these Fibonacci patterns. So here's our 1, 2, 3, 5, 8, and he found that 82% of the time you got Fibonacci numbers. And then, I don't know if you can see here, 2 times 1, 2, 3, 4, 5. That's another type of Fibonacci sequence. It's called a double Fibonacci sequence. So you just multiply each of these numbers. And then another sequence that he discovered was one called Lucas sequence. So it's related to the Fibonacci numbers, but it starts at a different point. And then there was another number pattern that he found in here called Fib4, something that he called it. And so anyway, here's the percentage of the time we saw it. So we were looking to kind of replicate that experiment. But what was interesting is if you look kind of down here, if you get lots of sunflowers, this doesn't happen very often. So what happens if we grew lots and lots and lots and lots of sunflowers? Would we get enough data to find some interesting things here? So we would expect to find Fibonacci numbers happening there, but what would happen if we grew lots of those sunflowers? So that was our goal really, to grow lots of them. And lots of school kids got involved in growing. We grew them at the Museum of Science and Industry. One of the beautiful things that happened with this project, which for me was one of its highlights, was how it made it into the kind of wider culture. So Manchester Day Parade, I don't know if anyone went, but there was this giant baby with the sun. Did I see that? Yeah. Okay, so some artists came along and planted sunflowers at Mosey, and they were making this giant baby anyway, but they got excited by the sunflower bit to it, and the baby ended up with this big headdress. And all the kids were dressed up in sunflower headdresses as well. I don't think they like that, but never mind. And then at Pride this year, what was fantastic for me was that the sunflowers had kind of made it into Pride that year and into the march. And I think there were 4 cheering sunflower floats. I didn't have anything to do with them, they just sprung up, it was fantastic. People gave out sunflowers at Pride, and also there was a housing estate, Eastland Homes. One of the things for me which I was really surprised with was that lots of people saw this as cheering sunflowers and celebrating it this year, as an opportunity to think about social responsibility and social justice. And to get involved in this experiment was a way to sort of deliver on that. So it was interesting, and to me it told me something about how times have changed. That you have a housing, people that own housing estates coming to you say, we want to get involved in this experiment because we want to make sure that all of our tenants in Manchester are aware of Alan Turing and his legacy, and that him being gay is part of that. I thought, yeah, that's pretty cool that's happening. That's not something that I knew about in 1980. And so anyway, coming back to the experiment, what was really exciting was I couldn't see what people were doing with their sunflowers. Were they still alive? I don't know if you know, it was the worst summer for growing sunflowers. Climate change, thank you very much, flooding, it was not good. So we had lots of sunflowers pledged. And anyway, we managed to prove this known link, again, between math and nature. People's made diaries of their sunflowers, put them online. And here's kind of what happened. 1897, they had just over 100. 1938, as you saw before, 319. And we managed to get around just under 600. So we managed to get a really big data set, which is fantastic. And very quickly, looking at the results, we discovered, so here's 2012, just over so about 82% of the time we found these Fibonacci patterns. But what was interesting is what happened in this bit here. So we also discovered, so we found the Fibonacci, we found the double Fibonacci, we found these Lucas numbers, but because people sent in photographs of their sunflowers, we also found that you can make spirals, but in a very disordered way. So if some sunflowers, it's very difficult to count the second Fibonacci count. And actually it wasn't a Fibonacci number. So there was something interesting there, which I think is relevant to thinking about diversity. There are different ways to make a sunflower, in the same way there are different ways to make a human. This is not something that I could do on my own. There were incredible partners involved in this project. and here's a whole bunch of them. This was my coming out. This is my pride costume for the day. One of the thing about legacy, I've now got this Wellcome Trust Fellowship, which is reflecting on projects that I've done and developing resources in the future. One of the things I wanted to do and involve people in here was thinking about how could we build this Turing's legacy into a school's curriculum to work with people to make that happen. So number one, get in touch with Amelia. If you've got other questions about the experiment, you can get in touch with me. And I need help later on today. There's this open session that you can come and just talk about all kinds of things. I'm on the debate later. I need help, man. This guy's got loads of evidence in his head, backed up, and I'm doing the challenging one, which is about discovering the gay gene. And yes, we want it. So I need help on that. So I'll be in that open workshop. Like, bring on popcorn.